Okay, this is David Zierler, Director of the Caltech Heritage Project. It is Wednesday, December 21st, 2022. I am delighted to be here with Professor Julia R. Greer. Julia, thank you so much for having me in your office. I really appreciate it.
Oh, thank you for coming and thank you for inviting me to participate.
All right, wonderful. Well, Julia, to start, would you please tell me your titles and affiliations here at Caltech, because I know you have many.
Yeah, I am actually a professor of all things that begin with an M.
Okay.
So I'm a professor of material science, mechanics, and medical engineering.
Okay.
I'm also a musician and a mom, so it all fits this
The
whole
five M's. I love it.
The M theme. Yes, absolutely.
And also, do you still direct the Kavli Nanoscience Institute?
Yes, so I actually have a few titles. So I'm an endowed chair professor, so I've got the Ruben and Donna Mettler chair professorship of all those things that begin with an M, as well as the Fletcher Jones Director of the Kavli Nanoscience Institute. So I guess it's an endowed position.
Right.
So.
And is there also an affiliation with the Chen Institute?
No, I have had funding and students that are involved in multiple centers on campus, like the Chen Neuroscience Center. We had a grant from them, and so we had collaboration and research in that space, as well as the Resnick. I'm very involved in the Resnick Sustainability Institute.
Right.
And I used to be on the board of directors, but I think they changed that structure, as well as the Rosen Bioengineering Center there, and KISS, Keck Institute for Space Studies. So I've been involved in
You're all over
a
the
lot
place.
of centers on campus. It's great. That's kind of what Caltech is. That's one of Caltech's strengths, is that it's so small, yet it's so impactful that it's very easy to form collaborations
Yes.
and to be interdisciplinary and to
Yes.
participate in all these centers and activities and thrusts that you normally may not even consider.
Exactly.
Yeah.
Julia, let's stay on the titles for just a second. So, Ruben and Donna Mettler. Have you met the Mettlers? Do you know their connection to either your research or to Caltech?
So what I know is that the person who held this chair before was Bill Johnson.
Uh-huh.
So he's a great colleague of mine, and maybe you did a
Not
stint
yet.
with him.
So he's emeritus now?
He's emeritus now, and
Okay.
so I actually was awarded this chair 2 years before I could tell anyone, because Bill Johnson hadn't yet retired. So from what I understand, Ruben Mettler was the CEO of TRW,
Uh-huh.
and I think he might not be alive anymore. I don't
Okay.
think so, but it's basically he and his wife that endowed this position specifically for material science. I think a professor of material science, possibly with a focus on mechanical properties, and
Okay.
that's what Bill Johnson did. He's a pioneer and a giant in the field of metallic glasses. And since there's a finite number of endowed positions, I kind of had to wait for him to retire for them to offer this chair to me. So
Yeah. Now, with the Nanoscience Institute, there's two benefactor names in there. Of course, there's Fletcher Jones and there's Kavli. So let's start first with Fletcher Jones. What is the Fletcher Jones Foundation?
So the Fletcher Jones Foundation is the lower, is a smaller participant. I think they probably contributed a bit to the endowment of the KNI. We call it KNI, the Kavli Nanoscience Center, but it is the Kavli Foundation that provided the initial endowment to get matched, I believe, by the Moore Foundation together, and then smaller entities came in to help out sort of along the way. So I think that the Fletcher Jones Foundation founded the directorship position, so it's a small contribution, whereas the Kavli Foundation oversees the center and contributes sort of a major part of its operations.
Now, the Kavli Foundation, they do astrophysics, they do all kinds of
And
things.
neuroscience.
Is this part of like a larger Kavli family of science? Are you connected with other Kavli institutes?
Very much. We are very much connected with them. So you're right, there's astrophysics, there's neuroscience, and nanoscience, and there are 17 or 18 centers, I think, around the world now. And Cynthia Friend is now the director of the Kavli Foundation, and I haven't yet met her in person, but she's coming here in February. So she took over, and there's going to be a 20th anniversary event, or series of events next year that we're planning this big celebration. So our Kavli Institute has been already functioning for 20 years, which is hard to believe. But yeah, we're very connected. There are assemblies in New York City, actually, where all the center directors go, and we, for the most part, most of the center directors know each other. And the Kavli Foundation itself hosts this assembly at the end of May, usually, where all the directors meet each other, and they come to visit all the institutes, and yeah,
And as director, how much of an administrative burden is that in any given week? Is it a lot? Are you able to compartmentalize it?
It's a lot. It's a big job.
Yeah.
I am super lucky because I have a terrific team. So I have an executive director, Tiffany Kimoto, and the director of technical operations, Guy Rose. And without those two, I wouldn't be able to do this job. So they're instrumental in running this. But it is a big job. It requires technical expertise, of course, because it's a big clean room. So Guy DeRose is running this big clean room operation, right? And I understand all this on the technical level. So when the piece of equipment goes down, or when we need to bring in a new capability or something like that, together with the executive function where we connect with the Kavli Foundation or we organize events. There are initiatives we participate in bigger, series of bigger initiatives from both academic standpoint as well as being liaisons to the foundation as well. So, yeah, it's a lot. It's a big job.
Does being director influence your research, the kinds of things you're interested in doing?
I wouldn't say that, no. I compartmentalize that. Yeah. It's a wonderful enterprise to run, and if anything, my management skills have improved tremendously since taking that over, just to I've learned one particular thing, for example, that it's important to elevate people, that people do better, not by being reprimanded, but by being placed in greater responsibility positions and just explaining that, and praising them in front of their peers. So I use those approaches to run my research group. But it hasn't influenced the types of problems that I tackle because that's very private. That's not private. That's very personal. I think each faculty member at Caltech really passionately cares about what we ultimately do and where that's going, and that's in part where our creativity takes us. And so that's something, one of the reasons why I rollerblade everywhere is it's my thinking time. It's when I don't belong to my students or to my kids, right? Because I am very needed everywhere.
You can't be caught.
You can't be caught. And so when I rollerblade, it's really making that space, creating that space to really think through some of the research questions that I may want to pursue, or some of the just reasoning through a particular direction and carving that out. And that's such a personal thing that I think knowing about what people do in the Kavli Institute is very interesting to me, but I wouldn't say it influences. It's more like it's broadening my sense of what's out there, but it doesn't influence.
All right, so we've covered administrative titles. Now let's go to discipline titles.
Sure.
Between, what you have in the title, the things that you work on, your educational trajectory, what aspects of your research agenda are more on the engineering side, and what are more on the fundamental science, the basic research side?
That's such a great question. I really love being a scientist, and
So that's what you are first and foremost, a scientist.
I think so, very much so. I really love this sense of discovery. So, yeah, the most rewarding experience to me from the research perspective is very much the scientific discovery and uncovering something that hasn't been known before and then trying to explain it, trying to uncover some phenomenon or observing some phenomenon, then making sure that it's real, right? Because when you're doing research, you're exploring, and so you don't really know what's correct, and so you have to double check and triple check that the data you're collecting is in fact meaningful, and then trying to explain it, trying to understand the mechanism that underlies a particular phenomenon. That's really satisfying to me. Then what we very often do in my group, and this is largely driven by students and somewhat by the funding agencies, is that now that we have this phenomenon and we kind of know how to explain it, what do we do with it, right? Like, how do we make use of it? And that's where the engineering part couples into the scientific part very naturally. So there's a clear synergy between the two, right? Because in material science, ultimately the whole world's made of materials. So what we do a lot in our research is we start with some very basic concept, either a molecular construct of some material that we chemically synthesize, or the atomic level microstructure, and then we build up in that sort of very basic atomic level microstructure into a material. And we do that through a series of processes. And then once it's a material and it behaves and it has, like a material has certain properties, then it's neat to be able to see where you can push the boundaries of what's possible today, and so that the engineering concept comes from making use of the phenomena that we uncovered. So I think first and foremost, scientists and then an engineer by, I don't want to say by necessity, but by curiosity.
In what ways do your engineering sensibilities or skills supercharge the discovery? How does it make the discovery, learning how nature works, more efficient for you to have that skill set?
Well, when you try to emulate something that occurs in nature, and when you try to build something that doesn't occur, it brings up a different set of I guess, thinking parameters, right? So how to make something work, you actually have to build it. Like you actually have to make a part, and then you have to make that part work. And very often we formulate a hypothesis, right? So I think it should work like this if you stimulate it like that. I think that something should curl to the left if you pull on it really fast, or it should curl to the right if you do it very slowly. So now that you know this, you sort of think of an application, you kind of force yourself into that thinking space where you say, like, well, where would that be useful? And then you say, well, something that morphs, right? Like something that more like an airplane wing, for example, right? So it could morph into a particular shape when during turbulence, and then it can unmorph when it's laminar flow. Or an example that I really like, we haven't made this yet, but I would like to make this. Say you're wearing a shirt right now, right? And this is a pretty lightweight shirt, and it's not very cold. But then if you, say, go to Boston or to New York, it's going to be really cold. So this material, we can build intelligence into the material itself, where it'll be triggered by, oh, the temperature outside is much, much colder. So it'll reconfigure the textile in your shirt such that it's as warm as a jacket without changing anything else. So you wouldn't have to change, right? And then conversely, you would go to Hawaii, and then the shirt would be too hot, right? And it would reconfigure itself to make it be porous. So the idea behind it, so this is something we're very much thinking about, how to build intelligence into material design at the fundamental level. So this is a very exciting area of research for us, and we're just starting to uncover it.
And intelligence, like artificial intelligence?
Like this, what I just described, like being able to make decisions based on the environment, right? So there's definitely a lot of artificial intelligence that we are now starting to explore. I don't know if you interviewed this professor, Anima.
Not yet. I'm going to get to her.
Yeah. So she's a great
amazing.
friend, and she's awesome. And we're starting to collaborate specifically on this. How can we teach AI how can we utilize AI to teach our materials as they're being built into a part to make that decision, oh, I'm going to be a good part, I'm going to be a bad part, or I'm being shaped like this, but I really should be going in this other direction. So incorporating that decision-making capability right as the part is being printed.
Does that mean incorporating computation itself into the materials? How is a material otherwise capable of making decisions?
Yeah, because we're making it. So additive manufacturing is a process where you're creating a part. So you start with some chemical resin, and then it's being shaped into a 3D architecture, or into a 3D part. So that's what I mean by that. So you start with something that's just chemically synthesized. And then we're using various 3D printing techniques to shape it into something that ultimately will serve a particular purpose. So during that process of being shaped, we want the part to either use images, I guess, as it's being shaped to make the decision for where to go next. Like say you're making a flower and you made one petal too crooked, and then the flower itself decides this is too crooked, I'm going to be a rocket instead, or something else. But being triggered, so as the part is being printed, being able to make the final call, am I going to be a good part or a bad part, or am I going to be something else from what I set out to be?
So you already mentioned the love of discovery. What about motivations for applied science, applications, translations of discovery into things that make human lives better?
Well, yeah, I kind of touched upon that. Are you looking for specific examples?
When you're specifically motivated by a societal need and you push your science in that direction,
okay.
What are some examples of that?
Well, I would say sustainability is a really big one. So we've been really working in batteries for some time now, right? Trying to get to the independent energy storage. But ultimately now we're much more excited about decarbonization. So removing the CO2 out of the processes that can be used to create steel, for example. So this is something where we're starting to work on. We have a collaboration with Harry Atwater and Karthik Manthiram on decarbonization of ammonia production. So ammonia, so there are something like 4 major industries that take up like 99% of all the CO2 emissions in the world. So one of them is cement. Another one is ammonia. I forget what the other 2 are, but these 2 are really big. And so, steel, sorry. So cement, steel, ammonia, and there's one more. So for the steel production, so what we've been doing is developing ways to 3D print metal parts using a certain chemistry, and it's entirely hydrogel based. So hydrogel means it's water based, right? So it's a lot less toxic than what you would normally use to produce steel. But now, when you produce these big vats of like in a big plant producing steel, their CO2 that's being emitted is just tremendous volumes of it, right? So you can look to other processes like electrochemical production or photochemical production, and I think that the ammonia synthesis that we're pursuing in that collaboration, I think it's relying on the photo initiated reaction to split water. So once you split water, you can sequester, the hydrogens that are being released, they can sequester the oxygen so that CO2 won't form. So that's one approach. But the way we're doing it is by 3D printing, you only make what you need. So when you utilize this additive manufacturing approach, you already are not wasting that much material because you're only making what you need to be making. And because it's a small part for the most part, you can actually capture the CO2 that's being produced. So without even this electrolysis or any kind of alternative processes. So even during the regular thermal treatment, you can capture the CO2 in the furnace where you're doing your secondary thermal treatment. And once you've captured it, you can reuse it or you can release it somewhere. But the point is that it's not being emitted into the atmosphere. So that's something we're very much interested in, is how do you make these additive manufacturing processes much more green, right? So that's a big societal need. So that's one. And then we've been working quite a bit in biomedical space. So making scaffolds for skin replacements, for example, or for any kind of a tissue replacement, right? So how can you make a much more integratable scaffold that's for bone, for example, for bone regeneration, or like for skin, so that you don't have to take a piece of skin from elsewhere in your body and then put it somewhere else, so that scar tissue wouldn't form, etc. So the idea would be, how do we create these 3D architectures where you can populate the cells onto it, and then the cells would form tissue, for example, right? And so understanding what is it that cells like or don't like, and why would, like, instead of using a hearing aid, you can just make the cochlea bone, right, and directly put it in the ear. So looking into ways of how we can help the body, I guess, how we can make artificial things, but that can be used directly in the body eventually, right? So that would be kind of a huge advancement. And another pursuit is we're developing lightweight armor, or lightweight impact protection.
Like better than Kevlar.
Much better than Kevlar, yeah. So the idea would be that our military personnel or any kind of protection personnel wouldn't have to wear these like super heavy bulletproof, or impact resistant jackets and vests and run with them, when it's really hot outside. So the idea would be to replace those with a much lighter, much more impact resistant material. So that they don't have to, because it's really actually very weighty. In fact, I had this amazing experience where we went to all the military bases and all kinds of military operations, from Fort Benning to Edwards Air Force Base and many others, and we shot guns with the Marines, and we got to participate in a lot of these military exercises, and it's a very impressive. And we had to put on all that gear, and it's very heavy. And when you're in Atlanta and it's 108 degrees and 100% humidity, you could faint. I mean, and soldiers really do. It's a very uncomfortable thing to deal with. So
because these technologies are very commercially exciting, where are you operating as a consultant? Have you thought about your own entrepreneurial venture, or is it just about coming up with the ideas and letting other people run with it? How do you deal with all of that?
Okay, well, that's a good question. So we actually started a little company. It's called Fugue, with my colleague Andre Farron, who's just my neighbor right there. So that's specifically to produce nano-architected sheets. So that pertains directly to the lightweight armor. So that would be a commercial operation, and at least we're hoping for. The idea would be that instead of making very tiny samples, so everything we work on is like nano scale and microscale. But nFugue is printing them as sheets. So you would have, like a 2-inch by 2-inch sheet, and then you can start making these platelets and incorporate them into the vest, for example, right? So they can also serve as filters. So right now, microplastics is a big problem in the world, right? So how do we make filters that can capture microplastics, right? So filters are kind of on our minds now that we're able to make nano-architected membranes, effectively, that can be chemically functionalized. So nFugue would be the enabler to be able to do that, so to produce the nano-architected sheets of paper, effectively. Right, so that's one. And then we produce quite a lot of patents. So I know we've licensed a lot of them. I know we've, people are really using them, so that's been exciting. So I wouldn't say, I do consult just as an individual to whoever reaches out, basically. But from the research perspective, so founding nFugue was one sort of a big step. And then everything else, it's through IP and through partnerships. And so the translational work usually comes through collaborations and partnerships with others. Do
you feel like you've been at Caltech long enough where you've seen this evolution towards ventures where professors want to do things like that? Has it become more common even since your time on the faculty?
I hope not. I want to say no. I think we don't like that. For the most part. I'm saying we sort of generically here, but I know many people went
the institute culture.
The institute culture is very much not like that. So I know that several people left for other universities, and then they came back, and it was specifically because there was so much pressure to be entrepreneurial. We actually want to do I'm actually quite happy doing fundamental research, and I think a lot of my colleagues share that passion for discovery and passion for doing the experiments and passion for uncovering something. Much more so than being translational. And I know many people, especially in, say, medical engineering, that's a new department, and it's a lot more translational oriented because it's kind of device centric. So of course when you're building devices, they're specific to targeting something or to actuating something, to enabling something. So people who work on devices, I can see that they would be a lot more maybe entrepreneurially oriented. But I think that the fundamental culture of Caltech is fundamental science, and I think that's something that drives us, and I think that that's something that unites us. And so getting that bug out of our, there are other universities. There's one very well-known university up north where where the pendulum has really swung in the entrepreneurial direction. Now everybody wants to leave. And so I know a lot of faculty members, have a lot of friends there who are really asking, how can we get to Caltech? We don't want to do this, right? Because then I think that being entrepreneurial is a great thing. If you think you invented some awesome technology that can really help people, that's awesome. All the power to you. But it shouldn't be expected. It shouldn't be an expectation, in my opinion. It should be something that you're passionate about, that drives you, and you go after that, right? It's not a university culture necessarily, but it's something that you care about passionately.
So it does raise the question of all the things that you could have created companies for. Why this one? Was it, like you said, because you made this discovery and you can just go with it?
No, that's also a very good question. We didn't want to start a company, but our investors convinced us to. It's an interesting thing. I didn't want to start a company, and my partner also didn't want to start a company, but we wanted to develop this technology. So I guess where I lose interest is when we've developed the technology, I don't have much interest in seeing it be made into a product.
Yeah, you don't want to do sales and marketing.
Definitely
and all
not.
That stuff.
And it's like I would love for other people to do it, and I would love to explain it to them or to be the scientific advisor and to hand them the technology, but I don't want to be. I'm not motivated by the problems associated with making product.
Yeah.
I worked at Intel for 3.5 years, so I know what it's like to make products, and it's like it definitely. I can see how many people consider that to be cool, but that's not for me. Oh, sorry.
Let's go to some history of technology questions now. So over the course of your...
Do you mind if we take a tiny break? Because
sure.
The AC is really cold. Are you cold or are you comfortable?
I'm okay, but...
All right, I'm going to raise...
Please.
I'm not used to my office being so cold. All right, we're good.
What have been some of the technological advances in the lab computationally that have really revolutionized the kinds of things that you're able to do since even graduate school?
Computationally?
Yeah, computationally or...
We're mostly an experimental lab. So we do computations to support our data, but we don't, we're not a computational lab.
So in terms of technology, in terms of maybe microscopy or anything else that just allows you to do the things that you do now that might not have been possible 20 or 30 years ago.
Oh, absolutely.
What kinds of technologies have come
What
online?
kinds of technologies? Yeah. So there's two that directly come to mind. So imaging, for sure. The microscopy has come such a long way. So when I was in grad school 20 years ago, it was a little less than 20 years ago. Okay, 18 years ago, the focused ion beam was this incredible tool. And I remember, so I did my PhD between 2 a.m. and 6 a.m. a lot of the days on that tool that's called FIB.
Just because that's when you can get the
Because
time?
that was the only time I could get the time. It was such a so it's called the focused ion beam, and it allows you to carve out micro and nano things out of whatever it is that you want, out of metals, out of polymers, but mostly metals. So you can carve out like a nano chair or a nano or micro object by basically removing atoms. So you start with like a cube of something, and then you remove atoms and material all around it to shape it into exactly what you want. So it's a very powerful technique. It uses ion microscopy and electron microscopy so you can visualize what you're making. But it was such a new thing when I was in grad school. There was one FIB for the entire university, right? So now I'm at the, and I remember, 2 a.m. to 6 a.m. is a rough shift, and I remember saying, someday I will have my own FIB. I'm like so fed up with this. So I have my own FIB now. I've had it for a while, and it was a huge
And is it
thing.
The same technology, or is the
no,
FIB
it's
itself
much more
improved?
advanced. That's what I'm saying. It's much more advanced.
In what ways? How's it improved?
Or the resolution has come tremendously a long way. You can really resolve things down to the nanometer level. This is true for all microscopy, for scanning electron microscopy or SEMs and transmission electron microscopy and TMs and FIBs, the focused ion beam. That technology has come so far, and so we're the kinds of images the kinds of materials that we're able to image, the quality of the images that you create, and the quality of the shapes that you make is tremendous. So that's one. The second one is additive manufacturing. That's huge. So we're using this process called two-photon lithography, or TPL. So it allows you to shape whatever you want. That's not subtractive. So you don't start with a chunk and subtract out the material you don't want. Instead, you add up. So you start with nothing, and then you build it up. So that's called additive manufacturing. That didn't even exist. Two-photon lithography didn't even exist when I was in grad school, and that's ultimately what we're doing. Like all these images that you see in my office.
What was the breakthrough that allowed additive manufacturing to come online?
Well, 3D printing, so just recognizing that when light interacts with photosensitive chemistries and resins, it provides a sufficient amount of power to cross-link that resin, and so that hardens it ultimately, right? And so you can imagine, now you have this voxel that's basically a very intense light pattern, and you can raster that voxel in three-dimensional space, and the material hardens where it's traveled, and it remains liquid where it hasn't. And so that's how I can write a nano U or a nano body or a nano rollerblade using that technology by recognizing that if you have a lower power laser than what we're used to, like the UV lasers is what it has typically been used for semiconductor processing. But now for 3D you have this voxel with a lower power laser, but they're exactly 2 photons per femtosecond pulse, and that provides sufficient amount of power to cross-link the polymer. And so I think so each one of these things has existed, right? Like the patterns of light, the cross-linking of polymers, and the 2D lithography. But I think combining all three of these concepts into recognizing that you can make 3D shapes was a big breakthrough. And so 3D printing didn't used to be a thing. Like when I was in grad school, nobody was doing 3D printing. But now, not only can you just have a 3D printer in your kitchen or in your garage, right? Like at every elementary school, you now have a 3D printer. They're much bigger. But that whole concept of using sort of a liquid starting precursor to solidify it into a particular shape, I think that is a major breakthrough, right? And it enables us to really think of materials in a very different light, because what we work on is adding that extra level of organization into material design, right? So ultimately all materials are made of atoms. And so the way the atoms are arranged, the way they come to their equilibrium positions, very much defines how materials are going to behave and what properties they have. And so we've been slaves to this coupling for centuries, basically always, right? So every material science book will show you, like, this is how you make steel, this is how you make cement, and then this is the atomic level microstructure that forms, and these are the properties. In fact, there's this quintessential material science triangle. It's called structure, properties, processing. So you process, and they're all three vertices are interconnected. So how you process defines the properties, how you process defines the structure, and then the structure and the properties are linked together. So they've always been coupled. And that's why everything is so heavy, right? Like all the bridges are heavy, all the buildings are heavy, because materials that are strong, that we know that their microstructure leads them to be strong, they're also very, very heavy. And so what we set out to do was to decouple these phenomena as much as we could, and that's where the architecture comes through. So that's an entirely new direction that I started after tenure, actually. So the idea is that you can build these intricate architectures that are bigger than atomic level scale, but they're smaller than what a human eye can see. So they're nanoscale. And so what makes them be nano-architected is these kinds of intricate three-dimensional lattices or patterns that you can build into the material. And now the largest dimension in these materials is just the width or the thickness of one of these individual nanoscale building blocks, right? Yet the overall material is as big as a room or a brick or something like that. And so it makes it be very lightweight. It makes it be full of air, but then you can still elicit the properties that you want. And so that's that extra organization that we build into materials that allows us to play around with it. And there's just so much to uncover that it's fun.
Julie, I loved looking at your academic lineage outside and all the centuries back that goes. It begs the question, how many generations back do you think you can go where the professor, the scientist, would see what you're doing, material science at the nanoscale level, and it would be recognizable to them? How many generations back do you think you can go for that?
Maybe 2 or 3. Yeah, definitely my advisor, definitely his advisor, and possibly his advisor. Do you notice I'm the only woman on that whole academic tree?
I did notice.
I mean, there's some, I think, since that time. I think probably, so
2 or 3 generations ago, what would be the dividing point? What did the fourth
microscopy.
generation? It's microscopy.
So I would say it's microscopy, yeah. So Richard Feynman, what was that, 150th anniversary, right, from There's Plenty of Room at the Bottom or something like that. So 150 years ago, they didn't have the microscopes that you could, they only had the optical microscopes, which are limited by the wavelength of that light, of that visible light, right? So you really can't resolve features that are much smaller than maybe a micron, and that's 1/1,000,000th of a meter, right? But now we're operating with nano scale resolution, right? So all of these scanning probe microscopy, scanning tunneling microscopy, transmission electron microscopy, there are all these much more advanced techniques where you can observe the behavior of individual atoms and understand them and visualize them so much better. So I think it's the development of microscopy, at least in materials science for sure, that has enabled so much progress in terms of understanding material behavior at these very small length scales, and turns out it's different. So physicists have been doing, quantum science for centuries. They've been doing electron-based studies for a long time, right? But these are all mostly, you can't see them for the most part, right? Like they either come through the data or they're theoretical for the most part, right? And these experiments are usually done at close to 0 Kelvin, and they're very tedious to set up, and they take many, many years, right? But like what we do is we make some material and we take it to the scanning electron microscope and we look at it like right away. So right away we can see features that are 100 nanometers or below, like that, every day, right? So that used to be such a big adventure, and now it's something that we do every day, and then we can base decisions for what to do next based on what we see, right? So we can deduce and do this iterative human learning, not machine learning, based on what we've made. So about 3 generations ago, I think, is when people started really delving into microscopy.
A technique that does go back very far, of course, is crystallography. Is
right.
that relevant for your work at all?
Very relevant, because crystallography implies periodicity and implies perfect lattice. But of course, materials are just like people. It's the defects that make them interesting. So we're very interested in the behavior of defects. And so crystallography is the number one branch of material science, and kudos to you for recognizing that. So X-rays X-rays are used a lot to understand crystal structure, but they can't explain everything, and they're particularly not effective to recognize defects. So you can even go to the synchrotron, like massive X-ray sources, and understand quite a bit about the construct, the crystal structure of a particular metal or a particular crystal, but you wouldn't be able to identify things like dislocations, for example, or point defects. And for that, you need to have transmission electron microscopy. So that's where the TEM comes into play quite a bit. And I did that a lot for my PhD, and I do that a lot still now. And it's just the amount of information you can get out of the crystallographic diffraction experiments, for example, is very valuable.
In running an experimental lab, are there theories from material science, physics, chemistry that are important for your work that might provide an intellectual framework to figure out what you're seeing?
They're 100%. I couldn't have even, yes, absolutely. The chemistry, the material science, the physics is all of that is the foundation of what forms a material, and we use that every day.
So what are some of the theories that are so important for your work?
Like the names of theories?
Sure.
So there's Hall Pedge, right? So that tells you about how the stress of a material depends on the grain size. So knowing the grain size in metals or in crystals is very important. There's so much dislocation theory. Like I teach a class on dislocations theory, right? So understanding everything about how dislocations move.
What is dislocation?
What's a dislocation? It's a dysregistry. So when you have a crystal lattice, all the atomic planes are perfectly aligned, right? So they're all, think of a ping pong balls and now connect them with toothpicks, right? So you can create these stacks of crystal. So imagine that each ping pong ball is an atom, and say they're equidistant from each other. And so they're connected into these planes, like egg cartons. And so the planes can stack up into ABC, 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 stacking, for example, right? And so you can see A, B, C, and then A. And so by the time you get from one A to the next A, they're going to be exactly one on top of the next one of each other. And then it's the next ABC, and then it's the next A. So there's a lot of periodicity. That's kind of what defines a crystal. So there's a lot of periodicity. In any crystalline lattice, there's always a three-dimensional degree of periodicity, and it can be more symmetry or less symmetry, but at the end of the day, it's still periodic. So what a dislocation is when you either take out an extra plane of atoms or insert an extra plane of atoms that doesn't belong there, and it terminates somewhere. So those kinds of dislocations actually what enables metals to be deformable. So the reason why we can bend a paperclip is because you're actually multiplying the number of dislocations inside. If every crystal were perfect, it would take a tremendous amount of force to bend, and then it would just break. So the reason why we're able to deform metals and to shape them into anything is because of the existence and motion of these dislocations. And they're defects. They're basically like ribbons or like little elastic bands within a crystal. And so we're very excited about dislocations. We really like dislocations. I teach a whole class in dislocations. There are a lot of theories actually. There's the entire dislocations theory is something that we use quite a bit to understand what formed them, what kind of dislocations are. There are different categories. There are screw dislocations, edge dislocations. They're how they interact with one another, how they're elastic fields. We use elasticity theory a lot of continuum mechanics type theory, linear elastic fracture mechanics, for example, and all the Hooke's law, like a lot of theories. Yeah.
A lot of theories.
A lot of theories. And then in chemistry, we use a lot of synthesis, like organic synthesis. And so there's click chemistry. There are a lot of theories as well that basically dictate how a certain polymer, like polymerization theories, like how a certain polymer should be made or what it depends on. And we work with a lot of theoretical collaborators.
Okay.
Yeah, a lot.
That's what I wanted to ask. So in physics, for example, there's a very clear divide between the experimentalist and the theorist. Right. Do you serve as your own theorist, or do you always go to the theoreticians?
We do both. So we're not, our theories are phenomenological. So the theories that we come up with is we look at the data, right? We do the experiments with a certain underlying hypothesis, and that hypothesis is always based on some theory, right? Or we're trying to debunk a theory, for example, right? Or somebody proposed a theory that we're trying to... what happens in theory a lot, at least in material science, is that somebody puts some theory out there, but it sounds good, but you don't really have a way to either prove it or refute it, because it's just not... It's not clear how you would go, because there's nothing, like how would you disprove it, right? So it's not like we set out a goal to debunk a theory, but it has happened several times where a theoretical paper would come out and they would predict a certain thing, and then we would do an experiment that would inadvertently either support that theory or would debunk that theory, right? And it's really exhilarating actually to do that. It's not really our goal usually, but it's just something that happens along the way. So when we're working like right now, we're working with we almost always have one or more theoreticians, colleagues that are working with us in a specific project. Because at some point, you can't really know, only based on the experiments, what's happening at the molecular level or at the atomic level. So when we make a new material, like right now, we're working on these, on this very unique class of materials that's called MPEC, or metal polyelectrolyte complexes. So the idea is that you have a polymer, and usually when you create a polymer and you process a polymer into whatever, like any polymer part, right? Like a wind turbine or a screen or a flower pot or anything, or like the sole of your shoe. It's set, like the bonds in that polymer are set. So they're usually called cross-linked. So they're either thermally set or through light activation, but that polymer is not going to change its properties unless you heat it up to some ridiculous temperature. But for the most part, they're set. So these bonds are very strong, and they're called covalent bonds. Now, in these MPECs, they're very interesting materials. They're still the polymer bone, and there are ions in there, but they're not covalent. And so they form and reform. And it's like this free will, like free love kind of a thing. These bonds can form, they can not form, and they can choose how to form, and they have tremendous properties. So like you can extend them by more than 1,000%. And then you can cut them and they'll self-heal. And then if you put a different metal ion, you wouldn't be able to deform it, to stretch it. So like if you put like nickel or calcium in there, for example, you can stretch it by 1,000%. And if you put iron or aluminum, you can hardly stretch it and it'll crumple. Same material. So trying to understand this, it's like, well, so we did the experiments, right? We kind of stumbled upon this. We didn't know that it was going to be different based on, it's called valency, based on a divalent versus trivalent metal ion. But we discovered this, and then we said, well, okay, this is kind of weird. Maybe we didn't do the experiment correctly. So we repeated it many, many, many times, and now we're discovering that, wait a minute, this is very much a real phenomenon, that this exactly the same polymer, when you put trivalent metal ions like iron and aluminum, behaves one way, and when you put divalent metal ions like nickel and copper, behaves entirely differently. And so we patented that. For example, we just submitted the invention disclosure. That's you can really do a lot with it, right? Because you can you can dictate at the molecular level what your material properties are going to be. So at some point we didn't know. We don't know how to explain that, and so we reached out to a collaborator here, Zhenggang Wang. He's a very well-known theoretician in chemical engineering, and who working specifically on polymers. And we reached out to him, and then we said, we don't know what's going on. Somehow the metal ions are coordinating differently with the polymers, and we need help. And so we're working with them very intensely, actually. They love this problem, and so they're discovering so much more. They're discovering their stress relaxation, their dynamic bond formation. There's just so many more questions that arose by partnering up with the theoreticians, and so it's a big project now. So theoreticians this happens a lot. We would discover something, we wouldn't mean to discover it, it would just kind of happen. We would do all the validating experiments to confirm it. We would develop our own hypothesis for what we think is happening, and then we would go to the theoreticians, and they would give us a million more questions to consider. But yeah, it's really fun.
Julia, a question on your interest in sustainability as it relates to this amazing gift that the Resnicks recently gave to Caltech. So, answering for yourself or just your general sense of the faculty at Caltech, are a lot of faculty members just sort of interested in sustainability, and the Resnick Institute has a centralizing force on this extant research? Or because there's this Resnick Institute, more people are getting involved in sustainability than they might otherwise have been had the Resnicks not had this amazing, generous gift? What is your sense of that dynamic?
Yeah, no, absolutely. I think there are multiple categories of people. There are some people who genuinely have always worked in sustainability, right? So a lot of chemistry. So many chemistry research thrusts directly feed into sustainability research just by its very nature, right? So trying to decarbonize the materials, for example, right? Or trying to come up with syntheses that are more green, and things like that. But then there are all these gray areas. For example, mechanical engineers who are working on lighter vehicles. Well, that is a sustainability problem, right? Because the payload that's required, the amount of fuel that's required, it's not the most obvious connection to sustainability, but it's still sustainability, right? Then you can think of photovoltaics, right? So like solar energy, very much a sustainability problem, right? So So all of that research went into that as well, right? Turbulence and flow, developing airplanes that are going to use less fuel, like not through the making materials lighter, but through more efficient wing design. Well, that's also sustainability, right? So I think that maybe what we're doing is we're redefining what sustainability means and maybe expanding it from the most obvious pursuits, which are generally chemical synthesis, catalysis, right? So how do you improve catalysis? How do you improve certain synthesis? How do you make things more in a more green way? Spreading all the way into alternative energy sources like batteries, for example, right? And of course, photovoltaics, and making much lighter materials, making much more efficient flow models, wind turbines, right? So each one of these problems is complex, and it requires this multidisciplinary involvement. So anything, like even in the photovoltaics world. So one thing is to make a device, right? But now with the Resnick Sustainability Institute, the problems are being enhanced by the translational aspect too. So they actually want us to make something that's a real product. And so there's a new building that's being erected here, and it's all going to be dedicated to translational research and to actually applying this, all of these discoveries and phenomena that we were just discussing to real products and to eventually being commercialized. So the Resnicks are very interested in commercialization and in the translational aspect of that. So I think that two phenomena happened. One of them is that many more problems that used to be only tangentially related to sustainability became defined as sustainability. That's one. Recycling, that was another really big one, right? So again, a chemistry problem. So recyclability, how do you get a polymer and then decompose it either back to its original monomers or to much smaller molecules that you're able to do something with, right? To recycle or to reuse them somehow. So polymer recyclability is a big direction as well. Right, so redefining and maybe enhancing the scope of what sustainability means is one, and then also being able to think about these problems from a much more translational perspective than only basic.
Now, for you and your interest in improving batteries, does that predate the Resnick gift, or was the Resnick gift the kind of thing where you thought you could get involved in this area?
It's a little bit of both. We're very student interest driven. So I keep on trying to get out of batteries, actually. But starting with maybe 10 years, I don't really remember my first battery student. When the new grad students come in, they often have ideas for what they want to work on. Yeah. And so this is pervasive throughout Caltech. So when a brilliant grad student walks in and says, well, I really want to work on X, in my case, this happens a lot, that they really want to work on batteries or on energy storage, on sustainability problems. I need to figure out a way to support them. Right, so unless they have their own funding, but more often than not, if they join my group or somebody's group, that advisor has to pay for them. Well, that funding has to come from somewhere. So it's generally the student's interest that drives our thinking to which funding agency we're going to apply. And so the Resnick has these internal competitions, which of course are so much easier than the external ones. Sure. And so it became natural to submit a proposal on batteries. Like for example, to create an all-solid state battery, right? So we don't have to deal with these liquid electrolytes that are flammable and dangerous and unsafe and all that. So, and we got that particular grant. We've had a few actually, Resnick grants. And so it's a chicken and an egg in multiple ways, but it ultimately begins with a student. So if a student comes in and they're interested in doing a particular battery-related research or sustainability-related research, it forces us, the faculty members, to apply for funding in that space if we like the student. Right, and so the Resnick just provides still this amazing opportunity for internal funding, and so it coupled together.
Julie, two last questions for today's talk. One is on science communication. TED Talks, interacting with journalists, appearing in the media. Do you do that because you're good at it, or you do it because it's fun? Do you do it because it's necessary, or is it some kind of all of the above? You're very comfortable in that space. That's obvious. So I wonder what your motivations are.
I was about to make a snide remark. Of course I'm very good at it. No, I'm just kidding. Well, I think it's necessary, actually. I think there's a huge gap between what the society sees in general and what they think of science and scientists and what is actually happening. And I think that the more accessible you make the science and the more human you bring to it, the more credibility I think we can attain, first of all, and the more inspiring we can be to the younger people to actually consider this. So the TED Talks make it possible for me to tell my friends who are not in scientific fields to be like, oh, you should watch my TED Talk and then you can understand what you do, right? Because right now it's this big unknown. It's like, oh, there's Caltech and it's a university and people that are really smart. And that's about it, right?
Yeah.
And it's like, well, I can actually explain to you what
Yeah.
I do
Yeah.
if you just if you could just focus, like, for 15 minutes, if you could just listen to this TED Talk, right? Or if you can give me a chance to explain this to you. And what happens very often is that people get inspired. When you explain it to, like, without being irritated, without being, I mean, it's annoying, but without, like, having that condescending persona, like, putting that aside. People
just being
actually,
a real person.
Just being a real person, it's inspiring. Like, hearing someone describe the kinds of problems that we work on and what remains unknown and how we tackle these things, it makes it more accessible.
Is there an added dimension as a woman to maybe reach girls, younger women who might say, "Oh, maybe I can go into that field"?
Maybe I can go that. I'm going to tell you a little bit of a story that happened. So one of my closest friends here is Frances Arnold, and of course she's a Nobel laureate, right? And so my girls, I have 2 daughters, and so my 2 girls, we hang out with her all the time. And then she got the Nobel Prize, and then I asked them, did that make the Nobel Prize more attainable, or did that make Frances more unattainable? Right? Like, which
great.
of the, right? Because the friendship has definitely changed.
Sure.
No matter what, like, we're still very close friends, but that definitely
the Nobel changes people.
The Nobel
profoundly.
really changes people, and it really kind of got to. It was an adjustment, I think, for all of us. And I think this is an important question to consider, that making we carry the responsibility. Actually, I'm not a Nobel laureate yet, but but nevertheless, I think we carry the responsibility of doing science right, and that means explaining it to the community, and that means carrying it forward in the most untainted way that we can, right? So we can't let it be corrupt, because if you corrupt something that's so data driven and that's so reasoned, we've got nothing, right? So explaining that, and explaining maybe in a way that is inspiring to maybe to younger girls, maybe just to people, but just to people, just to show that science is not bulletproof. It's not the way we teach our kids that there are answers at the end of the book. Math works that way, for sure. There's the right answer, and then there's everything else is wrong. But science really doesn't.
It just opens up a new portal.
Right. And actually, a good scientific project is when you start out with maybe one question that may be a little bit abstract, and after doing a few experiments, or after dabbling in that for a little while, it brings up a plethora of additional questions where you hadn't even anticipated, right? That's called exploration. That's how science works. And making mistakes is something that's part for the course, right? And pursuing these things and not being afraid of going into it, I think that's very much Caltech culture. So when there's pressure to be entrepreneurial, you are not giving yourself this chance to explore, because failure is not a thing these days, right? And our kids are growing up in a world where they're constantly judged. They're constantly judged on Facebook, or they don't use Facebook, on Instagram. Old people use Facebook. On every social media outlet, they're being judged by their peers in every way, and so they're terrified of failure.
Yeah.
I asked my grad students, we just went on a retreat, and I take my students on a retreat and we pose 3 questions before we go. And then when we go, we do this big hike in the mountains, and it's like this beautiful, beautiful place in nature. And then everybody sits down, and there's a safe sharing space, right? And what happens in a retreat stays in the retreat. And everybody comes and answers these 3 questions. And it was amazing. People are willing to go there. People are willing to share. And what comes right through is that they're very fragile. They're incredibly afraid of failure. These are brilliant Caltech students.
Yeah.
These are students who have nothing to worry about in life, yet they're so afraid. They're afraid that I'm going to think they're stupid, and they're afraid that they're afraid of failure. And I can't stress it enough.
You see that generationally? Do you not see that in your own undergraduate experience?
Not at all. We were all making mistakes, and we were all kind of there for each other. There was no fear. At least I don't remember being afraid, and I don't remember feeling like being a woman was something different. Like, I remember we were just all there together, learning and failing and getting bad grades together sometimes, and getting really good grades sometimes, and learning. Like, it was so natural. But now, especially when they say, well, we're afraid that you're going to think we're stupid. And I'm like, I'm your biggest advocate. Like, I'm the person who trains you academically to then go into the world. So that fear factor has to be removed. Like, I'm not there to judge whether you're stupid or not. I'm here to train you, right? So I need to see your data, and we need to talk about this data like colleagues, right? But that inherent sense of failure is pervasive in this, very much generational. I don't even see, this is new, even in the last 3, 4, 5 years, and COVID really didn't help. Like, I definitely see the difference between the COVID students who had to start anything, like either start school online, start college online, start grad school online. They're afraid to try things. They're afraid to be creative. For the most part, they're afraid of people. Like, they had to reintegrate into the social adaptation into the social world didn't come as easily to them. So I definitely see that, unfortunately.
Between COVID and fear of failure, these are both big problems for science.
They really are. And being able to explain, being able to interact with humans,
Yeah.
right? Just talking about it,
right,
and having a conversation. Right. Another thing I very much discuss with my students is that I can't be right 100% of the time. So you have to tell me, like, you have to say, I don't agree with this, or we need to have, situational conflicts that don't translate into personal conflicts. Sure. But a disagreement that is taken up, on the whiteboard, or that's taken up in a group meeting, and we may have a heated discussion, but you can't not argue. You can't not have disagreements, because, like, that's just not, you can't just be subservient. Yeah. And that culture of subservience, that's an enemy of science. So.
Finally, Julie, last question. Your music, do you wall that off from your scientific life? Do you integrate it? Is it part of how you see the world? Or are these sort of like two separate areas of your life?
Very much integrated. I actually just played a concert at my first graders elementary school. 2 concerts today. My day is not complete if I don't practice, and it's a huge part of who I am, and it's a huge part of my scientific thinking. It kind of sets it brings everything to being okay. I mean, it's a stressful job, right? I'm
Absolutely.
sure you hear this from
of
everyone.
Course.
Yeah. So it's a little bit, it takes time to process, and we all are being taught, you need to create space to process and to absorb all this information. But what working parent has the luxury of, processing or having time for self-reflection? Or
you have to get on your rollerblades.
I know, I have to get on my rollerblades to think about research. But actually, when I practice piano, I think that's that's when it all kind of settles in. That's when it all gets organized, and that's when everything, starts off with this very high entropy state where there's just like ping pong balls everywhere. It's like, these are the 83,000 things that happened to me today, and they're all in this disarray. And then when I practice piano, it kind of it self-organizes into something that I can process.
And that translates to better science for you.
That translates into much better science for me, yeah, because things are not chaotic. Every day is chaotic, right, with so much happening. And the expectation that we can just process it all. My favorite part is that when a student walks in and just picks up right when they left off, where they left off. It's like, Ruben, and I'm like, oh yeah, of course I know all 20 of your projects, like to intimate detail. And I don't. And so when I practice piano, whatever sense that music creates, whatever it is, everything falls into an equilibrium configuration in my brain when I practice. So they're integrated through the brain.
Julie, it's been an awesome conversation. I want to thank you so much. Next time we'll go all the way back, learn about your parents, grandparents even. We'll build the story from there.
Okay.